Okay, so these are the supplemental notes for the function inverse lesson, which is 10.6. Again, this is just to be something that is additional to the lesson already on Edgenuity. Okay, so this has to do with inverse functions, which we actually have already learned. So this should be a uh, lesson that you should know how to do. There are a few additional things that they ask you in the lesson, so I'm going to go over that. So an inverse function, it maps out the output values back to their original input values. The domain of the inverse relation is the range of the original relation. So all that we have to do is switch the x and y values. So inverse is the relation of the original relation over the line y equals x. Okay, so find the inverse. So all that we have to do, if it's giving you an ordered pair and it's asking, or a chart, and it's asking you to find the inverse, if for the x, it's going to be the y value. So instead of having a -4 there, it's going to be a 2. So we're going to have a 2 here, and then our next y value is a 1, then 0, 1, 2. Then the x value was -4, so our y value will be -4. Then -2, 0, 2, and 4. So let's just say that this question was asking us what would be their intersection points if we were to graph this. The intersection point would be the values that are exactly the same, 0, 0, 0, 0, because they would be the same point. So if they're the same point, 0, 0, 0, 0, then they would intersect because they do not change when we make the inverse. Okay, so verifying an inverse function. So we can, what we're going to be doing here, we've already done this, we're going to be plugging in one function into the other function, and if it gives us x, then it is an inverse. And then plug in the other function into the function, and if it gives us x, it is an inverse. So let's verify that these are inverses. So I'm going to take our inverse function here, all of this, and we're going to actually plug it in for x. Alright, so I'm still going to have a 2, but instead of an x, I'm going to put a 1/2 x plus 2. -4 on the outside because we're just replacing x, but the remainder of the problem stays the same. We're going to distribute our our 2 to 1/2 and 2 to 2. So 2 times 1/2 is 1, so 1x would just be x. 2 times 2 is 4. Not 2, 4. Then we have -4 here. Then 4 minus 4 is 0, so I get just x. So far this looks like this is an inverse. So now we're going to try it the other way around. I'm going to take this whole function and replace the x in this function. If it also gives me x, then they are inverses. So I'm going to have 1/2, and then instead of x, I'm going to have 2x minus 4 and plus 2. So we're going to distribute the 1/2, so I'm going to get an x minus 2 plus 2, and then -2 plus 2 is 0, so I just get x. So yes, these are inverses. Okay, so let's try it over here. So I'm going to take this function here and substitute it into the x. Okay, so we're still going to have 3, but instead of the x, I'm going to have the square root of x over 3, all squared. The square and square root will cancel each other out, and I have 3 times x over 3. Our 3's cancel each other out, and I get x. So far this seems like it's going to be a function, or inverses. So now let's plug in this one into this x. So here I'm going to have the square root of 3x squared over 3. Our 3's will cancel out, and I'll be left with the square root of x squared, which are x and x, or our square root and square cancel each other out, and I'm left with x. So yes, these are inverses. Okay, so all of this is a review, as well as this here is also a review. So finding the inverse here, we are going to replace f of x with y if it is an f of x. We're going to switch the x and y, and we're going to resolve for y. And then we're going to need to write this as the inverse. So inverse is f of the inverse of x. Let me redo that. Okay. F of the inverse of x. That's how it will be written. Okay. Kind of like it is up here. Alright, so let's find the inverse. So this one already has a y instead of an f of x. So now all I'm going to do is switch my x and my y. Then I'm going to solve for my new y. So I'm going to subtract 6 from both sides. Divide by -3. Everything is getting divided by -3. So I'm going to have -1/3 x plus 2 equals y. Then we're going to rewrite this as f of the inverse of x equals -1/3 x plus 2. Alright, let's try the next one. Alright, so f of x, we're going to change that to y. Then we're going to switch the x and y. And then we're going to solve for y. Subtract 2 from both sides. X minus 2 equals y squared. To get rid of the square, we square root. And I get y equals the square root of x minus 2. And then instead of a y, we're going to change that to f, the inverse of x, equals the square root of x minus 2. Alright, so all of this should have been review. So what they are saying that additional to it is if we're looking at graphs. So finding an inverse graphically, when you have an inverse function and you graph them, they are reflections over the line y equals x. Their points mirror each other, so the point AB on the original becomes the function BA on the graph of the inverse. So this one wants us to graph the inverse of these functions. So you could create a table. We have the point here, which is 0, 0. If we were to change that, so let's say our original here, and then our inverse. Alright, x comma y. Alright, well, let's start off over here with like 1, -1, -1, 1. Alright, so this will become 1, -1. So this point, let me erase this one down here. I want to do them in different colors. This point right here, when we mirror it, it will go down here. Then our next point, 0, 0. Let's do 0, 0, 0, 0. So that point would be the same. Alright, then if we do 1, -1, so that was this point here, it's going to get mirrored up to here. -1, 1. So these end up being the same line. So all other points would be intersection. So it would be all real numbers. Same line. But what if it wasn't the same line? The point of intersection would be the ones that are the same. same ordered pair. Like, for example, 3, 3, or 2, 2, or 1, 1. Okay. Okay, so functions and relations. So we've already learned functions and relations as well. So the domain are the x values, the independent variables, the range are the y values, the output, the dependent variables. Relations are all sets of x and y's, and functions are where the x values are different. So functions that have a 1-to-1 ratio here, they have inverses that are also functions. So what does that mean? That means that all the x values and all the y values are different. And because the y values are also different, that's why their inverses would be different. So it says which function has an inverse that is also a function. Okay, so here we're just looking at whether or not it is a function. So its y values need to be different. Or different. So if we have any that are the same, then no, that wouldn't be function. So this is going to be no, we have a 4 and a 4 here, so no. This, we have a 2, 4, 4, 2, so no. 3, 4, 14, 6, 2. Okay, so C, if we were to make this an inverse, so we were to switch them up, the x values would all be different because the y values are different. Right, so this one says identify the inverse g of x of the given relationship f of x. Okay, so we're just switching the x and y. Okay, so this would be here. Alright, so it says choose a true statement. Okay, g of x is not a function because f of x is not a function. Well, they are. This is a function. All my x values are different. Okay, so that's not true. G of x is not a function because the f of x is not a 1-to-1. Well, no, this is a 1-to-1. So because they are both 1-to-1, this is C. Okay. The vertical line test. So you can use the vertical line test to determine whether or not a graph and its inverse are functions. So if I were to draw vertical lines anywhere on this graph, a little bit better than that, then this would show that this is a function. The inverse is a function. If I were to draw a vertical line here, it shows that the inverse here is not a function. So if it's asking whether or not the inverse will be a function and it gives you a graph, you can do something called the horizontal line test. So the horizontal line test, like the vertical line test, if we draw the horizontal line here and it crosses our graph more than once, for example here, then the inverse will not be a function. Alright, so which of the graphs represents a function whose inverse is also a function? Okay, so because we're looking at a graph here, I'm going to draw a horizontal line. If it crosses in more than one spot, then it's not a function. So this is the only one that is a function. Its inverse would be a function. Remember, if you are having troubles on specific questions on this lesson, you need to email me, post them on the board on Canvas.